Ever ponder how miraculous it is that you even exist? Every cell in your body owes its existence to the mind-blowing fine-tuning of the universe, specifically the delicate balancing act of fundamental forces. Our cosmos runs on certain rules, laid down by fundamental constants that govern everything from swirling galaxies to jittery atoms. Here's the kicker. These constants are so freakishly precise that the tiniest tweak would annihilate any chance of life. Take gravity. If its constant varied by just 1 decillionth, poof, no you, no me, no anything. To grasp how tiny that is, consider your body is only around 10 to the 14th power cells, and the Big Bang happened roughly 10 to the 20th power seconds ago, and here it's about 10 to the 60th power.
Wow!
Same story with the universe's expansion rate. The merest deviation and life is toast. It's as if we're fiddling with billions of dials, and each dial must be locked in with insane accuracy. Everywhere they look, physicists see examples of fine-tuning. Martin Rees, UK Royal Astronomer and Emeritus Professor at Cambridge. Remarkably, the values of these numbers seem to have been very precisely tuned to allow for the possibility of life to evolve. Stephen Hawking, theoretical physicist and cosmologist at Cambridge. If anyone claims not to be surprised by features of the universe, they are hiding their head in the sand. These features are surprising and unlikely. David Deutsch, physicist at Oxford. Scientists propose 3 possible explanations for this fine-tuning. It's a necessity. The universe had to be this way. It's random. We just got incredibly lucky. It's the result of intelligent design. Which is most convincing? Look at the humble proton. If it were just 1% heavier, atoms would tear themselves apart. No matter, no you. Another shocker. The proton is insanely stable, outliving even the universe itself. Without that stability, no molecular synergy, no DNA. Meanwhile, within the nucleus, strong and weak forces keep it all from collapsing or burning out. A smidgen weaker or stronger, and we'd have cosmic meltdown. Astronomer Hugh Ross likens the chance of these perfect conditions happening to a hurricane ripping through a junkyard and accidentally assembling a Boeing airplane. Physicists call this the anthropic principle. It ranges from the modest notion, of course we see a life-friendly universe or else we wouldn't be here, to the bold stance that the universe was crafted with life in mind. As Freeman Dyson famously quipped, "It's as if the universe knew we were coming." Staring at these wild coincidences, it's tough not to ask, is there a divine blueprint behind it all?
What is he doing? He's beginning to believe.
This mystery has haunted the greatest minds for centuries. Even Isaac Newton, father of celestial mechanics, believed the elegance of his laws pointed straight to God's existence.
You're goddamn right.
Vera Kistiakowsky at MIT flat out says, "The exquisite perfection of the physical world requires the presence of the divine." And John Polkinghorne, a Cambridge physicist, got so awestruck he quit science to become a priest.
Fuck this.
Fuck.
But not everyone's buying that. Some see it as cosmic flukes, others see a deeper reason. The debate rages on. Nobel laureate Steven Weinberg says people crave a sense of cosmic purpose. We hate thinking we're just random accidents. But Weinberg dismisses divine design as empty mystical nonsense. Other physicists also scoff at the so-called anthropic principle. It doesn't predict or explain anything. It's basically, we exist 'cause we exist. Physicist Heinz Pagels calls it a disappointment. Alan Guth jokes that you invoke it only when you've got no better idea. But Cambridge's Martin Rees offers a different spin. Multiple universes. In most of these parallel realms, life is impossible. Protons decay, atoms never form, universes collapse or freeze. Our universe is just the lucky break among countless duds. So what used to be God's proof may be mere statistics in an endless multiverse. Rees highlights 6 crucial numbers that decide if life can exist, laid out in his book, Just 6 Numbers.
Did you see it? Did you see what? Wow.
That book, plus others on the topic, fed into this video's script. I recommend them all.
I like it.
From here on out, you'll see how the universe might spring from nothing, how quantum fluctuations spawn galaxies, if parallel worlds are for real, why the universe needs dark matter, why time flows forward, whether our cosmos came from black holes, and how cosmic natural selection might work.
What are you waiting for? Do it!
Picture a giant gas cloud in Orion, enough matter for 10,000 suns. One chunk glows from young blue stars' heat, another is dark and cold with swirling dust. Hidden in that darkness are warm blobs, future stars. Each blob has a spinning disk of gas and dust. No surprise, this is how every star forms. As the cloud shrinks, it spins faster, like a figure skater pressing his arms against his body. A star ignites at the center, leaving a disk that eventually forms planets. Bits of dust smack together into rocks, which gather into clumps, and bigger clumps into planets. That's how our solar system was born. Planetary systems abound across the universe, some with scorching hot Jupiters orbiting insanely close, others with super-Earths bigger than ours. Are they full of life? Life as we know it needs special conditions, a planet massive enough to hold atmosphere at just the right distance from its star so liquid water can pool, and a stable orbit to boot. There are billions of sun-like stars in our galaxy, each with planets. Odds are some of those are Earth-like, and here on Earth, life thrives even in boiling sulfur springs and deep-sea vents with no sunlight. We still don't know how it began. Maybe Darwin's warm little pond, maybe near a volcano, maybe in cosmic dust. Next door, we have Mars, where scientists keep hunting for life's traces and dream of shipping Martian soil home. But don't forget the icy moons Europa and Enceladus, which hide salty oceans under thick ice. Could be teeming with microscopic critters down there.
Yes!
If we find life elsewhere in our solar system, it implies that life emerges easily whenever conditions are right. Then the galaxy might be brimming with simple organisms. The rub, panspermia. Meteorites might shuffle life between planets, meaning all solar system life could share a single origin. Meanwhile, the SETI Institute scans the skies for signals from alien civilizations. Suppose they're also scanning for us. Even if we do find them, that conversation's going to be slow. Signals can take decades or centuries across interstellar space. Still, if we meet an advanced intelligence, we might find we share more in common than we ever imagined. Intelligent life may bear no intellectual resemblance to our own at all, but any beings that are transmitting signals to us must have some achievement in physics. If they have any powers of thought, they certainly share our curiosity about the cosmic event that brought us all into existence. They are likely to be interested in the structure of our universe, stars, galaxies, what is in it, how it is expanding, also its ultimate fate. This knowledge will become part of the common culture we will share with the aliens, and like us, they will note that a few key numbers are important to our shared universe.
Good.
Our universe is shaped by 6 key numbers. They dictate how fast it expands, how stars and galaxies form, and how life's chemistry plays out. Jiggle any one of them even slightly, and life goes kaput.
Well, if I'm going out happy.
Imagine a television set with 1,000,000 settings. In our universe, there are only 6, and if any is dialed wrong, you get the cosmic blue screen of death, not a show. Maybe there are multiple universes with different settings, and we lucked into the one with the correct ones. Kind of like living on a planet with just right gravity and temperature, but that's more metaphysics than science. So let's focus on what we can measure, those mysterious 6 numbers.
Status.
Gravity is the most baffling of nature's forces, hugely influential, yet insanely weak. It keeps planets orbiting, star clusters swirling, and cosmic expansion in check. No particle, not even light, can dodge its pull. Isaac Newton cracked its main secret. The same force that drops apples on Earth keeps the moon in orbit. If you double the distance, gravitational attraction drops by a factor of 4. But it's weird. Gravity runs the show on a galactic scale, yet it's the puny wimp among the forces. Take two protons, the electric repulsion between them is 1,000,000,000,000,000,000 times stronger than their gravitational tug.
I'm sorry, could you speak into my good ear?
This ratio is one of the most crucial constants in nature, labeled n. So why does gravity still dominate?
Tell him, Wash.
Because it only attracts. Unlike electric forces that can push or pull, all your body's plus and minus charges cancel out. But mass always adds up, culminating in formidable gravitational force for big structures. Size matters. On Earth, the bigger an animal is, the thicker its legs must be proportionally. If you scaled a mouse to elephant size with the same proportions, it'd collapse under its own weight. Meanwhile, a real mouse can leap from heights many times its size, no problem. In cosmic terms, if an object's heavier than Jupiter, gravity's so intense it can't remain solid, so it morphs into a star, a gigantic ball of superheated gas. At its core, temperatures soar to millions of degrees, and that searing gas pressure balances gravity. But imagine if gravity were just a little stronger. A universe where n is 1,000,000,000 times smaller. Stars would be 1,000,000,000 times tinier and live only a few thousand years, too short for complex life to evolve. Even an insect in that universe would need hulking legs, and human-sized creatures? Forget it, gravity would flatten them. Ironically, it's gravity's weakness that creates such a vibrant, diverse universe. It permits big cosmic structures to last and evolve. We don't know why n has its current value, but if it were off, we wouldn't be around.
Are you sure about that?
For 2 centuries, Newton's laws handled planetary orbits flawlessly. Then Einstein took Newton's gravity and doubled down. He showed that planets aren't really orbiting so much as rolling along straight paths in curved spacetime, like the sun warping an invisible trough, with planets hugging its rim. Einstein didn't disprove Newton, he leveled up. His theory explained not only planetary motion, but also what happens under monstrous gravity and near light speed. It unified space, time, and gravity into one cosmic tapestry.
What do we have?
In everyday life, you barely notice relativity. A flight might slow your time by 1/1,000,000th of a second. But where gravity roars, miracles happen. Take neutron stars. Imagine a star heavier than the sun, compressed to a city-sized ball with gravity 1,000,000,000,000 times Earth's. Bouncing a millimeter off its surface takes more energy than flying from Earth to Mars. Ramp that mass up even further, and the star implodes into a black hole, a pit so deep that not even light escapes. Around a black hole, space swirls like water down a drain, and time grinds to a halt. Millions of black holes lurk in our galaxy alone, each about the size of a small city, but packing 10 suns worth of mass. And at our galaxy's heart, a supermassive black hole, 2.5 million solar masses. Some galaxies house central black holes, weighing in at billions of solar masses. In contrast to the messy, complicated structures of stars and planets, black holes are eerily simple. All that defines them are 2 numbers: how much mass they've swallowed and how fast they spin. As Chandrasekhar put it, black holes are the most perfect macroscopic objects in the universe. Only space and time figure in their design. If you dared dive in, you'd watch outside time speed up until the entire future of the universe raced by in an instant. While to external observers, you'd freeze on the event horizon forever. In a star-sized black hole, tidal forces shred anything to atoms before hitting center. But supermassive holes, like those in galactic cores, might let you roam for hours. The theory even allows for tiny black holes no bigger than an atom, each weighing as much as a mountain, possible relics of the Big Bang's earliest moments, bridging the cosmic and quantum realms.
Whoa.
Black holes smack us in the face with the boundary of our understanding. At their core, known physics breaks, and space-time itself collapses. Studying these cosmic traps might finally yield a theory merging the macro and micro laws of nature. Now, jump back 13 billion years. No carbon, no oxygen, not even iron. Just hydrogen and helium in a bare-bones universe. Looks hopeless for life, right?
Well, see you later.
But the cosmos was craftier than that. In that apparent emptiness, the first stars erupted into existence, not just ordinary balls of gas. All stars are cosmic factories. At their blazing cores, where the heat soars into the millions of degrees, alchemy happens. Hydrogen fuses into helium, unleashing monstrous energy. That is why stars shine. Our sun looks eternal, but it's been powering Earth for 4.5 billion years already. Don't be fooled. This story's got an end. When the sun's hydrogen finally runs dry, our gentle star will morph into a red beast. Its fiery outer layers will balloon, possibly engulfing Earth. If not, the scorching heat will evaporate oceans and obliterate all life. Then the sun will puff off its outer skin and shrink to a white dwarf, a ghost of its former self. But that's mild compared to the wild drama some stars face. Look at Orion. Those brilliant, hot blood giants weigh in at 10 suns and shine thousands of times brighter. Their cores run so hot that atoms fuse into heavier and heavier elements, hydrogen into helium, helium into carbon, onward and upward. But once they hit iron, that's the kiss of death. The core collapses to city size, and the star's outer layers blast outward in a cosmic fury, shining like billions of suns for weeks. That's a supernova, one of the universe's most cataclysmic fireworks. In that inferno, elements up through uranium get forged. The debris screams outward at 20,000 kilometers per second. In 1987, astronomers watched such a mega blast up close. A star 20 times heftier than the sun detonated, becoming the brightest nighttime object for weeks. These destructive events actually built our world.
How?
Every single atom in your body, apart from hydrogen, was born in long-dead stellar furnaces. Carbon, oxygen, iron, all gifts from stars that died eons before our solar system was even a thought. We're not just stargazers, we're star children.
Got him!
But none of this cosmic drama and the life it spawned could have happened if one tiny number, the Greek letter epsilon, hadn't been exactly right. That number is 0.007. Without it, we wouldn't exist.
What?
During hydrogen to helium fusion in the sun's core, 0.007 of the mass transforms directly to energy. You might say, so it could have been 0.006 or 0.008. No way. At 0.006, stars wouldn't forge new elements. No carbon, no oxygen, just bleak, hydrogen-filled nothingness. At 0.008, all hydrogen would have burned in the universe's first minutes, leaving no fuel for star formation and no water for life. Both scenarios, game over. The real jaw-dropper came from physicist Fred Hoyle, puzzling over carbon's genesis. By normal calculations, carbon just shouldn't exist. You'd need 3 helium nuclei to collide in an ultra-precise cosmic dance, like flipping 3 coins and having them all land on edge. Hoyle figured there had to be a special resonance enabling this, and he nailed it. If certain cosmic numbers were off by a mere 4%, that resonance wouldn't happen. There'd be far too little carbon for life to emerge.
You must continue your journey without me.
What are you? What? Whoa, hey.
Picture the Milky Way on a clear night. What you see is just the edge of our galaxy, a colossal, swirling disk with at least 100 billion stars. Our sun hangs out in a tranquil patch about 25,000 light-years from the galactic center, orbiting the central black hole at a sluggish pace. One full loop takes 200 million years. A galactic year, astronomers say. 2 million light-years away sits our cosmic neighbor, Andromeda. She's creeping toward us, set to collide in 5 billion years. Simulation footage looks like doomsday, but fear not. Stars are so spread out they'll simply rearrange into a brand new, bigger galaxy. This collision is part of a grand-scale shuffle. Galaxies bunch into groups, groups form clusters, and clusters organize into webs. The nearest example is the Great Wall, a cosmic network over 500 million light-years long. And that's not even the biggest. There's a megastructure called the Great Attractor, tugging us in hundreds of galaxies at hundreds of kilometers per second. You might think this pattern just keeps repeating endlessly, fractal style, like endless mountain ranges or jagged coastlines. But it's not that simple. After about 700 million light-years, the universe smooths out like a calm sea. This uniformity isn't random. If galaxies had been arranged any other way, we'd never get stars and planets. If matter were too uniform, you'd have an infinite void of diluted gas. Yet, from minuscule irregularities at the Big Bang, we ended up with a cosmic tapestry of galaxies. In 1929, Edwin Hubble spotted the universe's expansion. Distant galaxies recede from us at speeds tied to how far away they are. No, we're not the center. Every alien in every galaxy sees the same. Space itself expands, but galaxies don't stretch like taffy. They're just zooming apart. Gaze at the stars and you're peering into the past. Light moves fast, but not instant. From the sun, it's an 8-minute trip. From our galactic center, 25,000 years. From the most distant galaxies, billions. The earliest galaxies we observe appear as they were when the cosmos was barely a billion years old, and by the time that light reached us, the universe had swollen sixfold. But what about before galaxies ever formed?
Okay.
The biggest clue is the faint cosmic heat enveloping everything, a uniform microwave glow, akin to your microwave oven's output, but vastly weaker. This background radiation is the real echo of our cosmic birth cry. It proves the entire universe was once a sizzling orb, hotter than a star's core. Even now, every cubic meter of space contains 412 million photons, ancient light particles from that primeval fireball. Compare that to a measly 0.2 atoms in the same volume. In other words, for every single atom in the universe, there are 2 billion photons, bearing witness to our universe's fiery infancy. In the first few minutes after the Big Bang, the temperature soared beyond 1 billion degrees.
Oh, that's hot. That's hot.
Fast forward 500,000 years, it cooled to around 3,000 degrees. That was a game changer. Electrons, which had been tearing around freely, finally latched onto atomic nuclei, birthing the very first real atoms. Before that, the universe was this thick fog, but now it turned transparent to light. And something else crucial happened in that cosmic dawn. About a quarter of all hydrogen fused into helium, which is why even the oldest stars and galaxies sport roughly 24% helium. That's one of the prime arguments backing the Big Bang.
Why?
But forget the mental image of a giant explosion at some point in space. That's wrong. The expansion has been and is happening everywhere, all at once. No single center for matter to rush away from. Each point in the universe can equally claim to be the start.
Jeez, is that true?
That's delightful.
Sure, we've gleaned a lot about the Big Bang's early minutes, but what's next? Will our universe expand forever or collapse back in on itself? That fate hinges on one big parameter, omega, the ratio of the actual density of the universe to the critical density. If omega tops 1, the universe's expansion eventually reverses, leading to a cosmic collapse. If omega dips below 1, it expands forever. That critical density is easy enough to figure out, about 5 atoms per cubic meter. Cross that line and gravity can halt the expansion. 5 atoms sounds tiny, but the real cosmos is even emptier.
First of all, this is a terrific presentation.
If the sun were shrunk to an orange, its nearest star would be 10,000 kilometers away. Spread all visible matter evenly, you only get 0.2 atoms per cubic meter, 25 times below critical, so you might guess eternal expansion. But it's not that simple. By the end of the 20th century, scientists realized that what we see is just the tip of the cosmic iceberg. Most of the universe's mass is invisible. We call it dark matter, and it only shows itself via gravity. How do we know it's there if we can't see it?
You have questions?
Yes.
Astronomers studied star and galaxy motions. They were spinning too fast, far faster than visible mass alone would allow, so something massive and unseen is holding them together. Turns out dark matter outweighs ordinary matter by about a factor of 10, but it can't be just burnt-out stars or dust, because we'd notice those. Probably it's exotic particles that barely interact with normal matter, ghosting right through Earth and your body without a trace. Right now, billions of those weird particles might be zipping through you.
You what?
Physicists are trying to catch them in specialized detectors buried deep underground, but so far, no luck. Still, if they succeed, it'll blow open a new realm of physics. Meanwhile, the omega question hangs unresolved. Normal matter accounts for just 5% of the critical density, dark matter another 25%. Still not enough to reach 1. Something else is dictating our universe's fate, something that might rewrite our cosmic destiny. Ordinary atoms appear to be a minority in the universe. They are surrounded by swarms of particles of various kinds that survived the first moments of the Big Bang. But far more puzzling is the question, why are there any atoms at all? Why isn't our universe composed solely of dark matter? Physics tells us each particle has an evil twin. Protons meet antiprotons, electrons meet positrons, and when they collide, their mass morphs into pure energy, annihilation. Scientists can create a speck of antimatter in particle accelerators, makes an ideal rocket fuel, 100% mass into energy. By contrast, nuclear fusion yields less than 1% mass conversion, but antimatter hardly exists in nature.
How'd that get in there?
Our entire galaxy, stars, gas, dust, is mostly regular matter. Why is that weird? If we started with equal amounts of matter and antimatter, they'd have nuked each other into oblivion. So something broke the balance in the early universe. For every billion matter-antimatter pairs, there was one extra particle, a 1 in a million mismatch. All we see around us today comes from that tiny leftover. Meanwhile, each 5 cubic meters of space has 2 billion photons from that ancient mass annihilation and just one lonely proton. That's crazy. The Soviet genius Andrei Sakharov cracked this puzzle in 1967. Suggesting that early on, physics laws gave slight preference to normal matter. Physicists James Cronin and Val Fitch confirmed certain particles and antiparticles decay differently, but the mother of all fine-tunings is about omega. In the universe's first second, omega had to be exactly 1 to 15 decimal places. The tiniest bit above 1 and the universe collapses back. The tiniest bit below 1 and everything blows apart too fast for stars to form. Picture tossing a bottle off a 20-meter drop and having it land upright. That is the level of cosmic luck. Why?
I had a lot of questions. I'm sure you had a lot of questions, but rest assured, we're going to answer them right now.
What the fuck is this piece of shit?
Measuring the expansion rate changes of the universe is like CSI on a cosmic scale. We need a standard candle, something with consistent brightness. Quasars? Too erratic. Galaxies? Too messy. But nature gave us supernova, the perfect cosmic nuke that always explodes with roughly the same power, shining for days brighter than its entire galaxy. Spot one, and you can gauge its distance precisely. Measure its redshift, and you know how fast it's racing away. Compare near and far supernova to see whether cosmic expansion slows or speeds up. In the 1990, 2 teams launched a supernova hunt. Catching the faint glimmer of blasts from billions of years ago was mind-blowingly hard. By 1998, both groups had over a dozen distant supernova. The result rocked astrophysics. Instead of slowing from gravity, the universe's expansion is accelerating. It's like some mystery force keeps pushing galaxies apart, harder and harder. Science magazine crowned it the discovery of the year. Turns out there's an unknown power outrunning gravity, later branded dark energy. The universe's accelerating expansion implies something wild about reality. There must be an extra force providing cosmic push, even in a vacuum. So, we have to add another key number describing this anti-gravity's strength. The void is one of physics's deepest riddles. Even if you scrub the vacuum clean, cool it to absolute zero, yank out every particle, there are still hidden forces inside. That insight led Einstein to propose the lambda number. Back in 1917, Einstein was wrestling with relativity, but folks believed the universe was static, no expansion, no contraction. Physics said a static universe should cave in under gravity, so Einstein introduced a new cosmic repulsion, described by lambda. 12 years later, astronomers discovered the universe is expanding, making Einstein call lambda his greatest blunder. Had he not added it, he might have predicted the expansion. But ironically, time showed Einstein messed up twice.
You know what? Is that actually happened?
Once by adding the force, and again by ditching it.
Who the fuck are you?
70 years on, lambda crashed back into physics. Turns out empty space teems with hidden energy, particles and antiparticles popping in and out of existence, a roiling quantum froth. But here's the paradox. Quantum theory says the vacuum's energy should be so colossal the universe would have shriveled to a measly few kilometers long ages ago.
That's kind of small. Yikes.
Observations reveal that the actual lambda is 10 to the 120th degree times smaller than theory predicts, the biggest fail in all physics. Scientists didn't hold back. This is the worst theoretical prediction in the history of physics. Two things keep expanding: the universe itself and our ignorance about its vacuum energy. For ages, physicists assumed lambda was zero, no cosmic repulsion. Then, astronomers spotted something peculiar in the cosmic microwave background. They saw tiny lumps, seeds of future galaxies. This sizes implied lambda wasn't zero. In fact, it had to be around 0.7, a gigantic value for a force once deemed non-existent. That discovery shook our vision of cosmic destiny. Sure, on the scale of stars and planets, gravity still reigns, but in those vast intergalactic gulfs, lambda calls the shots. Project forward 100 billion years, and the universe's fate depends on that small number Einstein once dismissed as a mistake. If it's non-zero, galaxies will keep flying apart faster and faster. The very error Einstein introduced will ultimately govern our cosmic finale. Will we remain part of a boundless cosmic web, or become lonely islands drifting in emptiness? Nature and art teaches that the most stunning creations are never purely orderly or purely chaotic. They strike a perfect balance between the two. So it is with our universe. We see a crazy, diverse cosmos, blazing stars versus frigid voids, dense galaxies versus thin intergalactic space, 118 chemical elements plus an endless array of molecules, all from a once uniform, white-hot early universe. The mastermind? Gravity, with a twisted trick. A star that loses energy and contracts actually gets hotter at its core. That's how scorching stars can arise from a cold gas cloud. In Orion, you can watch it happening right now. Roll back time to 500,000 years after the Big Bang. We had a fiery soup. If it had been perfectly uniform, it'd still be that way today. Just expanding, thinning, cooling. But in reality, there were tiny lumps, bits slightly denser than average by 100,000th, the so-called Q number. Gravity pounced on that minuscule difference, amplifying it like a spark starting a blaze.
Very impressive.
Dense spots slowed expansion, grew denser, and eventually reversed to collapse under their own weight, forming the very first galaxies. Stunningly, we can still see the fingerprint of these lumps in the cosmic background radiation. Some spots show a tiny temperature rise, matching precisely that Q equals 100,000th. Were Q much smaller, no galaxies could form. Were it much bigger, everything would clump into monstrous, super dense lumps.
Yeah, boy.
Either way, no stars or planets, no life. Q equals 100,000th is the real showstopper, a signature trait of our universe. The fact that the Q number is only 100,000th is actually the most amazing characteristic feature of our universe. If you pick up a ball-shaped rock with an accuracy of 100,000th, you might of course wonder what caused the fine inhomogeneities, but you might be even more surprised by its near-perfect smoothness. The Q number is basically a cosmic recipe shaping the consistency of our universe, a recipe that's unbelievably precise.
Nice.
Our world is rigged for life. Take the number of spatial dimensions. Exactly 3. That's no coincidence. In 1D, creatures would be like beads on a wire. You couldn't even bypass another object. In a 2D paper world, you can't form complex structures. Try building a digestive system without slicing through the surface. With 4D or more, you get even uglier problems. In 3 dimensions, gravity and electromagnetism drop off with distance in just the right way. Double the distance, force weakens by 4. That's the inverse square law, perfect for stable orbits. Any more dimensions and forces would fade too fast. Planets would spiral into stars or fling off forever. Heck, even atoms would disintegrate. Electrons couldn't stay bound to nuclei. Then there's time, the 4th dimension. Unlike space, we only move forward in it, sparking a paradox. The fundamental laws of physics don't distinguish past from future. The asymmetry between past and future is so firmly entrenched in our minds that few people, apart from some philosophical physicists, stop to ponder the riddles it poses for us. It is disconcerting because such asymmetry is not built into the basic laws governing the microcosm.
Good.
If you film 2 billiard balls colliding and reverse it, no biggie, they look normal, but ramp up the number of balls and irreversibility emerges. Where from?
You have questions?
Yes.
Imagine viewing time from outside like Kurt Vonnegut. Aliens see humans like wormy centipedes, baby at one end, old man at the other. From that vantage, the universe is a frozen 4D block. The past is orderly, the future is not. But why have any order at all?
Right.
Like spotting a gorgeous pattern at one end of a rope. It's a miracle it exists, never mind which end it's on. And remember, universal expansion ties tightly to the flow of time. Early on, the universe was so dense and hot that collisions were constant. Time was almost meaningless. As space stretched and things spread out, time began to matter big time. Imagine if the universe had expanded more sluggishly. Then practically all atoms might have turned into iron. Thank goodness the expansion rate was high enough that only a quarter of the hydrogen became helium, paving the way for our crazy variety of elements.
Now I feel better.
Physicist Julian Barbour once asked his colleagues, which is fundamental, time or something else? Most said time isn't fundamental at all. It's like temperature, which you can reduce to atomic motion. But the truth is, we simply don't know. The riddle of time stays unsolved. Meanwhile, our galaxy alone houses millions of black holes, gnarled knots where space and time wrap together. Yet on cosmic scales, the universe looks pristine and nearly uniform. The relic radiation's temperature testifies to that. Could that smoothness be a trick? Maybe our cosmos has a kaleidoscopic geometry, or labyrinthine honeycomb structure spanning hundreds of millions of light years. If it's any smaller, we'd see repeated patterns of galaxies in the sky. Observations say, if there's a hidden honeycomb, it's at least as large as our visible domain, which is mind-boggling. Beyond the cosmic horizon, space could be bizarre in ways we can't even imagine, possibly with extra dimensions. But no telescope can pierce that cosmic boundary set by light's speed. We can try peering into the microcosm. Just as matter is built of atoms, space-time itself might have a granular structure. We can't see it, just like we can't see actual atoms with the naked eye. At some point, there's a hard wall, the Planck length, 10 to minus 35th degree meters, which is 10 to 20th degree times smaller than a proton. The smallest time interval, Planck time, is how long light needs to traverse that Planck length. At these scales, the known physics collapses. That's where quantum mechanics and relativity smash together, and we haven't figured out how to unify them. In day-to-day life, it's no big deal. Quantum effects matter for atoms, gravity for planets and stars. But in the Big Bang's first instance, or a black hole's center, both run the show simultaneously. Space might be frothy, time might run forward or backward. Testing that is fiendishly hard.
Tell him, Wash.
It's incredibly hard.
You'd need energies far beyond current colliders. The only natural lab is inside a black hole, but nobody's itching to volunteer for that suicide mission.
Oh, hell no!
So physicists scramble for alternatives. One is superstring theory, a mind-blowing ambition to unify all forces of nature under one elegant framework and to show how gravity works at the quantum scale. In the 1980s, Stephen Hawking bet someone that we'd soon have a theory of everything. Didn't happen. He lost that bet. The core concept of superstring theory is straightforward. All fundamental particles are actually tiny vibrating strings. Different particles?
I gotta tell you.
Just different notes on these sub-Planckian guitars. But these strings aren't thrumming in 3 dimensions. They need 10. Where the heck are those extra dimensions lurking? Physicists Kaluza and Klein pitched an idea a century ago. Extra dimensions may be curled up into minuscule corners, like a sheet of paper rolled tight. From afar it looks 1D, but it's actually 2D. In superstring theory, every point in our 3D space hides a labyrinth of 6 extra dimensions, coiled down to Planck-length scales. The entire makeup of our world hinges on exactly how these hidden dimensions are folded. But the math is so insane that even the top-tier geniuses break a sweat trying to solve it. Then, in 1995, a bombshell dropped. The curling up can happen in exactly 5 ways. Turns out it's not just 1D strings. There are 2D membranes and higher dimensional branes. Then the killer twist. These equations spew out a mind-boggling number of solutions. Something like 10 to the power of 500 possible universes. What the fuck does that mean? Maybe out there, far beyond our reach, fresh universes pop into being all the time. We inhabit just one of the freakishly rare universes with decently rich matter structures. This fits the ancient pattern. Whenever we think we're unique, we find we're part of some cosmic set. Long ago, we believed our village was the whole world, then discovered new continents, new planets, new stars, each step showing us a bigger, more diverse reality. But the multiverse concept ups the ante. Other stars and galaxies we can still see and test. Other universes, by definition, we can't. Welcome to the boundary of science itself. Because science is about testability, reproducibility, measurement, and parallel universes are beyond all that. Every solution to string theory is an entire universe. There appear to be infinitely many solutions. To test our theory, you'd have to create new universes in a lab. In other words, only God can run that experiment. This theory is about entire cosmoses, not just atoms. String theory says there could be an infinite number of parallel universes, many so freakish they'd blow sci-fi's mind. Maybe a universe where protons are unstable so matter rots into electrons and neutrons. No atoms, no molecules, end of story. Some folks think these universes are just math illusions, but the real snag is the theory can't tell us which one is real. And that's not a glitch unique to string theory. Any theory of everything is bound to slam into the same wall. That's the cosmic game, folks. The deeper we dive, the wilder the puzzle gets. Even classic equations like Newton's or Maxwell's have infinitely many solutions. For a light bulb or a laser, we pin down a single solution because we know the starting conditions. But for the entire universe, good luck. It irritates physicists. We want the theory itself to dictate the initial conditions, temperature, density, composition at the Big Bang, rather than leaving them as inputs. Can string theory predict our universe? Sure, but can it predict only our universe? Seems not. That's the so-called landscape problem. So why do so many physicists swear by a theory we probably can't test experimentally? Because it elegantly merges Einsteinian gravity and clarifies black holes. In 1996, Andrew Strominger showed black holes can be viewed as swarms of strings, matching Bekenstein-Hawking predictions exactly. Another string-based forecast is mini black holes, which might be tested with particle colliders someday. In the early 1980s, physics hit three unsolvable roadblocks. One involved magnetic monopoles. Theory said they should exist, but no one found any. Another was the universe's mind-blowing flatness, as if someone dialed its parameters with insane precision. The third puzzle asked, why is the cosmic temperature so uniform everywhere, given that different regions never had time to communicate? Then along came Alan Guth, who answered all three with the notion of a false vacuum. Early on, all the forces were unified, like water backed by a dam ready to collapse. Once a microscopic crack formed, that dam burst. The universe blew up in a fraction of a second, ballooning by factors of trillions. This cosmic inflation outpaced even light speed. One tiny, uniform patch of space expanded to become the entire cosmos.
Did you see this? Look at this.
Father, think of the child.
This brainchild tidied up those mysteries like a cosmic broom. Magnetic monopoles? They're scattered so thin it's like hunting a needle in a cosmic haystack. The universe's flatness? It's been stretched so far we can't see the curvature. Just like Earth appears flat locally. The same temperature across the sky? Because everything we see originated from that same tiny, uniform region. Physicists around the world immediately grasped the importance of Guth's discovery. Nobel laureate Marie Gell-Mann exclaimed, "You have solved the most important problem of cosmology." Another Nobel laureate, Sheldon Glashow, told Guth in confidence that Steven Weinberg was furious when he heard about inflation. Guth excitedly asked, "Did Steve have any objections to the theory?" Glashow replied, "No, he just wished he had thought of it himself." Yet cosmic inflation triggers new questions. How did it begin? Maybe it sprang spontaneously from quantum fluctuations in empty space. And the juiciest riddle, if it can happen once, can it happen again and again, spawning infinite universes, each with its own bizarre twist on reality? Andre Linde rocked the physics world with a bold notion. Inflation might not just flicker on and off, it could roll on forever, spawning countless bubbles of space. Each bubble forms its own separate universe. Some bubbles collapse instantly, some never spawn stars, but in a lucky few, like ours, everything lines up just right for galaxies and planets to be born. They call this eternal inflation, where it's like a messy cosmic garden sprouting infinite universes. Sure, some physicists think that's overkill, but quantum theory itself begs us to think this big. If the early universe was ultra-tiny and prone to quantum jitters, there's a tiny chance one universe can bud off another, and so on, branching endlessly, each bubble with its own cosmic laws. One can, of course, object to the notion of a multiverse because it seems that its existence violates laws known to us, such as the laws of conservation of matter and energy. However, the entire energetic, material content of the universe may actually be very small. The material contents of the universe, including stars, planets, and galaxies, are enormous and of positive magnitude. However, the energy hidden in gravity may be negative. If we add the positive energy of matter to the negative energy of gravity, the sum may be close to zero. In a sense, such universes are free. They can jump out of the vacuum with virtually no effort. In fact, it might take a ridiculously small amount of matter, perhaps as little as 1 ounce, to create a universe like ours. As Guth is fond of repeating, the universe might as well be a free breakfast. Yes, a universe from nothing might sound nuts, but there's a logic to it. Some forces add up to zero. Positive matter energy canceled by the negative energy of gravity, letting it pop from vacuum to vastness. Physicist Edward Wrighton believed exactly that. The creation of the universe is an event that happens from time to time. Picture building a hill by scooping dirt from the ground. In the end, you have a hill positive and a hole negative that net to zero.
Wow.
The Big Bang created a mountain of positive energy while conjuring an equal negative chunk stored in space-time itself. Think of it like the universe borrowed energy from gravity, like space is one giant storage battery for negative energy. No deity required. Then how did it all begin?
How?
Well, in everyday life, nothing emerges from nothing. But in the quantum realm, where subatomic particles spontaneously appear and vanish, that's normal. Initially, the entire cosmos was smaller than a proton, so it could have manifested as a quantum fluctuation without busting any laws, then expanded, building more and more room for negative energy. Not only do the laws of nature say that the universe can suddenly emerge unaided, like a proton, but they don't rule out the possibility that the Big Bang had no cause at all. None. We're used to the idea that everything must have a cause, but for the universe, that logic breaks down. Time itself was born with a Big Bang. Asking what happened before time is like hunting for the edge of the Earth. No edge, no point. This bizarre concept is starkly evident in black holes. They're so massive they warp not just space, but time. A clock dropped into one slows ever more as it nears the event horizon, until, bam, time itself halts inside that black hole. It's basically a time killer. And guess what? The Big Bang is like a black hole in reverse. It's the moment time started. Naturally, not everyone is sold on the notion of a multiverse. It's untestable, critics say, but more and more cosmologists see it as the most sensible explanation for cosmic fine-tuning. If countless bubble universes exist, the lucky break that ours came out just right for life is no big shock. Then we're left with a new question. If there are millions of different versions of reality, are our cosmic six numbers just a lottery win? Or is there some deeper reason for them? Martin Rees calls a limitless ensemble of universes the simplest fix for our lucky constants. If there are many suits in a store, it's not surprising to find the right one. If there are many universes with different laws of physics, it is not surprising that in one of them the laws turned out to be suitable for life. Even Steven Weinberg, famously skeptical, likes the idea that universes pop into being eternally rather than spontaneously out of nothing just once. But the boldest multiverse spin might be Lee Smolin's cosmic Darwinism. Think of universes reproducing like living organisms, forging new universes inside black holes, each child inheriting physics laws from its parent with minor tweaks. The universes that churn out the most black holes replicate the most, like a cosmic survival of the fittest. Why might that also be good for life? Because the same conditions that maximize black hole production also yield robust, long-lived stars, forging carbon, oxygen, and other life-friendly elements. So maybe we inhabit a cosmic apex predator among universes, a champion breeder of black holes. In the theory of disordered inflation, daughter universes are characterized by physical constants somewhat different from the mother universe. If universes can arise from black holes, some physicists believe that the universes with the largest number of black holes will dominate the multiverse. This means that, as in the animal kingdom, the universes that give rise to the greatest number of children eventually become dominant and spread their genetic information, the physical constants of nature. If this is true, then our universe could have had countless ancestor universes in the past. In other words, our universe is a byproduct of the survival of the fittest, which means it is the child of the universes with the most black holes. Lee Smolin claims we can test it, just count black holes. Our universe should be near a local maximum. Any tweak to the constants and we get fewer black holes. Cosmological natural selection plausibly explains why the parameters of the standard model are fitted to a universe filled with long-living stars that have enriched it with carbon, oxygen, and other elements over time. This explanation assumes that black hole production is maximized, and the consequence turns out to be habitable conditions. Under cosmological natural selection, our universe is a typical representative of a population of universes, and there is no room for a customizable principle.